Today we're going to start Unit 4, which is all about exponential functions. And the first learning target in this video says, or in this unit, is I can determine if a table, graph, and situation can be modeled with an exponential function or a linear function or neither, something different. Now if a function is linear, then we know that the change in y or f of x has a constant difference. We'll call that the first change. Okay? So if you were to find, for example, all the differences here, they should all be the same. And if they are, it's a linear function. We already learned that if the function is quadratic, then the second change has a constant difference, and we'll talk in a second about what that means. Now, if the function is cubic, then it would be the third change. Would be the one with a constant difference. So you would take the change once, take it again, and then take the differences of those. And if those are all the same, then it's a cubic function, the third change. And this pattern continues for all polynomial functions. If you need to keep taking the differences over and over and over again, and you get the same constant things after the fifth time, then it's a fifth power function, a quintic function. Okay? Now, that's how it works for polynomial functions. If it's an exponential function, then the change in y, or really that's like f of x there, the change in y or f of x has a constant multiplier. Okay? So let's look at some of these tables and see what we're talking about, because right now you might be feeling a little bit confused about this, but I think it'll all get kind of cleared up in these tables. Let's look at this first table. From 4 to 7, that goes up 3. You could also look at that as you could say 7 minus 4 would give you 3. It's always the one below minus the one above. So 10 minus 7 gives you 3. 13 minus 10 gives you 3. 16 minus 13 equals 3. And 19 minus 16 equals 3. So because my first change, the first time I tried to find all the differences, I got all the same number, I know that this is a linear function. Because if my first change is constant, then it's a linear function. Now let's look over here. 7 minus 5 is 2. 10 minus 7 is 3. 14 minus 10 is 4. 19 minus 14 is 5. And 25 minus 19 is 6. So I know my function's not linear because my first change here, my first set of differences, is not constant. So now let's take the second difference, the difference of all of these. 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. 6 minus 5 is 1. So because my second set of differences is all the same number, that means my second difference is constant, or my second change is constant. So that's a quadratic function, the second power. Because if the function is quadratic, then the second change will all be constant. Now let's look over here. If we take the differences here, we get 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. 16 minus 8 is 8. 32 minus 16 is 16. So we know it's not linear. Let's do it again. 2 minus 1 is 1. 4 minus 2 is 2. 8 minus 4 is 4. 16 minus 8 is 8. Not quadratic. And you might see a pattern developing. This is never actually going to even out. These differences all just reflect these numbers. 1, 2, 4, 8, 16, 1, 2, 4, 8. And it's going to do the same thing again. 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4. And it's going to keep doing that. If this table continued, we could keep going out for forever and we would never have a constant difference. However, we're going to write nope here and come up with a different plan. Exponential functions have a constant multiplier, so let's do that. We could think of this with multiplying, or we could think of this as dividing. Just like you could think of this as you have to add 3 to get to 7, or you could think of this as 7 minus 4 gives you 3. If we find that constant multiplier by dividing, just like we always subtracted, we would say the one below minus the one above. Here, we're going to do the one below divided by the one above. So 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. So because it has a constant multiplier there, it's exponential. 1, you times it by 2, you get 2. You take 2 and you times it by 2, you get 4. Times 2 is 8, times 2 is 16, times 2 is 32. It just multiplies by 2 each time. Now let's try that same multiplying pattern over here. 81 divided by 243 is 1/3. Okay? 81 divided by 243 reduces to 1/3. 27 divided by 81 is 1/3. 9 divided by 27 is 1/3, right? 9 over 27 reduces to 1/3. 3 divided by 9 is 1/3. 1 divided by 3 is 1 divided by 3, that's 1/3. Okay, so all of these, if you take the one below and you divide by the one above, you end up with a bunch of fractions that all reduce to 1/3. So our constant multiplier is 1/3, and because it has a constant multiplier, we know that this function is exponential. Now let's look at these graphs. What we're going to do is we're going to make a table based on these, using these points. So our f of x, here, -1, 1 is my first point. The next point is 0, 2. The next point is 1, 4. The next point is 2, 8. So let's see if it has a constant multiplier. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. So when we divide all of these, we end up with a constant multiplier. So this one is exponential because it has a constant multiplier. Now let's look over here. F of x, we have -2, 1. Looks like -1, comma, up 2. 0, 5. 110. Okay? This one, let's look to see if it has a constant multiplier. 2 divided by 1 is 2. 5 divided by 2 is 2.5. So it doesn't have a constant multiplier. So let's go back to adding. Maybe it's linear, quadratic, one of those. So now we're subtracting. 2 minus the one above is 1. 5 minus 2 is 3. 10 minus 5 is 5. So it's not linear. So we know it's not exponential because 1 times 2 is 2, but 2 times 2 is not 5, it's 4. So it doesn't have a constant multiplier. It doesn't have a constant first difference. 3 minus 1 is 2, 5 minus 3 is 2. It does have a constant second difference, though. So because it has a constant second difference, we know that that function is quadratic. Now, we've talked about graphs, or tables. We've talked about graphs. And our learning target says that we need to look at tables, graphs, and situations. So let's think about a situation. If you are deciding whether or not a situation is exponential, make a table to model the situation, and then figure out the pattern of the table, just like the examples above. So here's an example of a situation. On a countertop, there is 1 bacteria remaining after you chop up some raw chicken. Each hour, the amount of bacteria doubles. What type of function models the growth of bacteria on this counter? So, f of x. At the beginning, we start with 1 bacteria. Then it doubles every hour. So after 1 hour, there are 2 bacteria. After another hour, now that's doubled, now there's 4. After another hour, now that's doubled, so now there's 8. After another hour, there would be 16, and so on. So let's see what kind of pattern this is. We can start looking at to see if it has constant differences with adding and subtracting. Maybe it's like linear, quadratic, cubic, one of those polynomial functions. Or we can see if it's exponential by seeing if it has a constant multiplier. This one does have a constant multiplier, and we can find it by dividing. So 2 divided by 1 is 2 if you divide that. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So you can see that this has this timesing by 2 pattern. 1 times 2 is 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. So because it has this doubling pattern, it is an exponential function. Okay? So that is how you determine if a function is exponential or not. If it's exponential, it has a multiplying pattern. If it's one of these polynomial functions, linear, quadratic, cubic, then it has an adding pattern, either with the first change or the second change or so on. So now go ahead and start your quiz.